Hello everyone, welcome back to another video session on the subject EC308 Embedded Systems for the 6th semester ECA students under KT University. We have been discussing about real-time operating system in our previous session. We came to discuss the features and the various functions of real-time operating systems and the classification of operating systems. This session and the coming session will be about one particular operating system, the MUCOS operating system. The MUCOS is one of the most popular real-time operating system. It is a freeware operating system for non-commercial use which was developed by Jean J. Labrousse in the year 1992. MUCOS has been used to develop a number of applications, and their name comes from microcontroller operating system. The MUCOS is derived from the word microcontroller operating system, and they are also known as the MUCOS or micro COS or UCOS. So in our session we shall be repeatedly calling them as the MUCOS. The MUCOS is a portable, ROM-based, scalable, preemptive, real-time and multitasking kernel. And they have found applications in various industries such as the automobile industry, the avionics, consumer electronics, military purposes, aerospace purposes, medical devices, networking devices and a number of SOC devices. And this MUCOS, they have very customized codes, and they offer the best high quality performance ratio. So because of all these reasons, MUCOS has been greatly preferred for a number of applications all around. So even the source code of MUCOS has been certified by the Defense Department of USA for the specific application in avionics and medical application. And MUCOS has similarly received a number of certification from international associations, whether it be the European based associations or American based association. So they have been, the MUCOS real-time operating system has been recognized by all the departments all over the world, and it has full source code availability. So this makes MUCOS acceptable for all the programmers, and the MUCOS codes are in C, which is another great advantage of MUCOS RTOS. The MUCOS also provide additional support for building blocks for hardware devices such as for clocks, for LCD displays and so on. They also has a flash memory loader, file system, memory file system. They support all these things, GUI platform, real-time monitoring tools, the embedded TCP IP stacks. So the MUCOS has additional support for all these devices. They also have additional support for CAN buses, the embedded mode bus for the USB device framework. So see, the way the MUCOS can connect to all these type of external devices make them very preferable to all the fields of use. Now we shall see what are the features or main features of MUCOS. The MUCOS employ a preemptive scheduler for multitasking. Preemptive means we know that before the task completes, when a higher priority task enters, the task can be temporarily suspended. So the MUCOS employs such a preemptive scheduling for multitasking, and thus each operating system as well as the user process, they have clearly distinct priorities. So that, and there is a proper scheduling of these priorities and this multitask in MUCOS. And MUCOS is a scalable OS operating system, which means that there are necessary there are certain portions of the application codes which can be used only when necessary, and because of which the system has a reduced need for memory. And these functions they need which we need for task servicing, interprocess communication and others, they can be and must be predefined in the configuration file of our real-time operating system. And then these files can be included with your user codes too. The MUCOS file level functions are for initiation and for the start of real-time operating system, and the system clocks interrupts, their ticks, the clock ticking, they can work as the interrupt, and their system level functions of MUCOS, they can be used for initiating as well as starting the real-time operating system. And the critical sections of your MUCOS code can be handled by any of the three methods, which are this MUCOS has a capability of disabling and enabling interrupts for handling an ISR code, and two functions are ISR enter and exit functions, and these functions execute while entering the ISR section, and the ISR exit is used while exiting the ISR critical section. So one way of handling the critical section is by using two sets of ISR, one for entering and one for exiting the section. Another way for handling the critical section is by using a scheduler locking and unlocking function. So this is similar to the ISR enter and exit function, just like that. So this locking of the scheduler, this disables task switching, because you are already in the critical section. So once you enter the critical section, the scheduler locking is done, and while you are exiting the critical section, you are unlocking that scheduler. So this makes sure that your system doesn't switch between different ISRs. So they lock the system to a particular critical section, that's it. So one method is by using the ISR enter exit, another is the scheduler locking and unlocking, and the third way is by using semaphore functions. So here we are using semaphore functions as mutex functions, and they also execute just like entering and exiting the critical section. So any of these three ways MUCOS can have a good control over the execution of their critical section, and this is a great advantage of MUCOS. Apart from this, the MUCOS has a set of task service functions which create the task, run the task, suspend and resume the task. So this helps in an efficient implementation of the task schemes. And the MUCOS has two delay functions, two task delay functions, and this helps to generate a delay for a higher priority task also. And when you delay a task for certain period, this enables your lower priority task to execute. And once your delay time is almost done, your delayed process or delayed task can be resumed. So the two task delay functions makes even the higher priority task to be delayed. And when these higher priority tasks are delayed, the lower priority task can be executed. And later on, the delayed task or the higher priority task can be resumed just as usual. So these two task delay functions helps the MUCOS in enabling or giving a delay even to the high priority task. Another feature of MUCOS is is common to most of the real-time operating system, that is memory allocation function. So they can create and partition your memory into blocks, just like it's done for other operating systems. And once this memory is made into block, they can get the block details, put data into the block, codes in the block, debug the code in the block. They can do all the functions with respect to that memory. So MUCOS also enables memory allocation functions. Another very important feature of MUCOS is their inter-process communication, IPC functions. And this IPC function basically use semaphore, queues and mailboxes. So these are the three very important IPC functions in MUCOS real-time operating system. And see, these semaphore functions in MUCOS, they can be used like event signaling flags, and you can be used as sharing resource acquiring keys or counting semaphores. Any of these functions can be used for semaphore functions in MUCOS. And MUCOS also has this mailbox functions. So all these helps MUCOS in executing this IPC functions in a great manner. And the MUCOS mailbox, they have one message pointer per mailbox, and there can be a number of messages, as MUCOS sends only the pointer, which is the starting address of the message, into the mailbox. So that's how the MUCOS mailboxes work. And they also have the queue functions. The queue functions in MUCOS, they allows an array of message pointers per queue. For every queue there is an array of message pointers specified, and there can be any number of messages in a queue element. In a single queue there can be a number of messages, because see, this MUCOS, as we have mentioned earlier, they basically send the address for just they just send the address of the message into the queue. So there can be a number of messages. So these are about the features of MUCOS. In the coming part of this session and the coming video sessions, we shall see the source file and very important functions which are being used in MUCOS. So to begin with the source files of MUCOS, see, we have already discussed, see, as we started with MUCOS, we said that they have a beautiful set of codes. First of all, the codes are in C languages. So which means most of the programmers are familiar with the C languages, which makes MUCOS pretty handleable. It can be handled well by the programmers. Now this MUCOS has about 10,000 lines of codes, and there are two types of source codes, which are the processor dependent and the processor independent. And just like any C file, they have the hash include header files, the preprocessor commands. For both the types are there. So let's just have a very brief idea about what are the processor dependent source files and the processor independent source files. So the two header files for the processor dependent source files are as given here. So the first one gives you the header files, and the second configuration file, CFG file. These are the header file for your kernel, to build your kernel. Similarly, for the independent source file, see, we won't be having a hands-on session on this, yet you just have to familiarize with, okay, these are the common source files or codes which are used in MUCOS. That's the sole purpose of this session. Okay, like I'm not giving in very detailed idea about it, but yeah, these are the things that are used in MUCOS source files. That's it. Okay, fine. Okay, the other set of source file is the processor independent source file. So here, as you can see, these are like general type of files which doesn't depend upon whether you are using an ARM processor or any other kind of processors, 80510, whatever be your processor, that doesn't matter. So they basically have these codes for memory partitioning, for semaphores, for queues, mailboxes. The good thing about it is that most of your file names, these can be relatable. So they have a systematic naming convention for these files, and because of which it is pretty easier to understand these codes and even the files. So basically the convention they follow is, there is a OS, operating system, OS followed by an underscore. So when these are used as prefix, and it denotes that the function or variable is a function or the macro or variable in MUCOS operating system. Because we have this functions like OS task create. So this is a function which creates a task. So similarly, it's easy to relate the function names with the actual purpose of the function. It's because of this very particular naming convention that they follow. Right. Our next purpose is to familiarize with the various functions in MUCOS. Here we shall see in the system level function, the task level function, memory management related functions, semaphore related functions, and so on. In this session we shall start with the system level functions. So at the features, while we were discussing the features, we already said that the system level functions, they are related with initiating and starting the operating system. So what are the system level functions that we are using? So they involve initiating and starting the operating system, initiating the system clock, starting the operating system timer, and scheduler functions. The second set of system level function will include for handling the ISR and the critical sections and preemption related to it. The third set will be the disabling and enabling of interrupts. The fourth one, locking and unlocking the scheduler. And the final one, get and set the time functions. So in fact you can see that the disabling, enabling, interrupt, locking, unlocking, scheduler are the ways by which your operating system can come out of the critical section. So all these functions come under the system level functions. So we'll have a quick look into what are the functions that we use for all these tasks. Let's begin with the initiating and starting the operating system. So definitely when we are starting an operating system, our first duty is to initiate the function of our operating system. So what is that function that we use for it? You use the function OS_init, initialization, in void brackets, for initiating the system. And once that is done, you use the function OS_start with empty braces for starting the operating system. So these two functions helps in initiating and starting the operating system. So the main function, they will do the initiation. They will create at least one task, and this first task is called the first task or the start task, and this then starts your MUCOS. So when your OS start function execute the first task, only the task of highest priority, they will start execution. And the first task, once they get created, they will create the semaphore and other IPC functions. So what has happened so far? Our operating system has been initiated by OS_init function. Then it has been started by the OS start function. So when this initiation is done, they will create the first task, and this first task will create the semaphore and other IPC functions. Later they will start the ticking function. So we have done the initiation starting, then we have to initiate the clock ticking, right? So this first task will execute the function of the OS tick initiation, which means you are initiating your clock tick, right? And this tick enables switching of processing from user mode to supervisory mode, which is the kernel mode, at constant intervals. So there is a constant switching from user mode to your supervisory mode, right? And this function, the OS tick per second, they will specify the interval. See, so far all the functions that we have seen, OS init, OS start, OS tick init, see all these we are able to at least guess what does that function perform. OS init, initialize the OS, OS start, starting the operating system, so on. So this beautiful naming convention of MUCOS enables us to understand these functions pretty easily. Now let's see the list of functions that are used for RTOS initialization, starting, system clock initialization, and so on. So the function OS init, they are used to initialize your system. OS start for starting the initiated system, right? And they will create the first task, and it is this first task which will then later create the semaphore and the IPCs. Then you have your OS tick init. What is the purpose of it? To initiate the ticking of your system clock, and it is based on this ticking we are able to switch your working from user mode to the kernel mode and continuous switching in particular intervals. These intervals are related by this OS tick initialization, and the intervals are defined by OS tick per second function. So that's how the first set of initialization and starting the operating system is done, by using these three functions. Once that is done, our next job is to handle your ISR and the critical sections. So how is that being done? So again, your MUCOS, they have a set of system level functions for handling your critical section and ISR. Now what are there? They are the OS int enter, int exit, the OS enter critical, exit critical. So even without explanation, I guess you could at least guess what might be the function of all. See, the first function, OS int enter. So they are used at the starting of an interrupt service routine. Enter, you are starting the ISR. And this is used for sending a message to your RTOS kernel that the ISR has taken control of your processor, and this has started executing. So int enter, you have entered your ISR, which means the kernel gets a message that ISR has taken control of your processor and has started their execution. And it's use is very compulsory to let the multitasking of operating system kernel, and this can be used to control the nesting of ISR in case of multiple interrupts of various priorities. So this is when you start or when you enter an ISR function. Just like that, you will have to exit from the ISR function, and for that you will have your OS int exit. So you exiting from your interrupt service routine in the operating system. So what message does the operating system get? They get an idea that the ISR is exiting the control, or the ISR is quitting the control from their loop. and it is again compulsory to let the operating system kernel quit the ISR from their loop, and they won't return any parameter. It's just a message to your operating system that okay, I have done my task, I have completed my task, right? So we had two functions to signify that I have the operating system has given their control to your interrupt service routine, and similarly you have this function to realize that your interrupt has exited from your loop. Next function that we have is the OS enter critical. So this is used at the starting of a critical section in a task or even ISR, and this is used to send a message to the kernel, and this helps in disabling the interrupt. It's the use of this function, it's very compulsory to let the operating system kernel take note of and disable the interrupts of the system, because you have already entered the critical task and other interrupts are disabled. Similarly, you will have a opposite mechanism which can be used for enabling interrupts, that is the OS exit critical, which is these are used just before the return from the critical section. So this gives you a message that see your RTOS kernel has completed their control from the critical section. They are now free to welcome any other interrupts. So this section will enable the interrupts in the system. So these are the four functions: entering and exiting your ISR, entering and exiting your critical section. When you enter your critical section, other interrupts are disabled. When you are about to exit your critical section, other interrupts are enabled. So these are the four things that happen when you are controlling a ISR, right? So this was your second system level function. The first system level function was related to initiating and starting the operating system. So you had to initiate, start and initiate the ticking of your system clock. So those three tasks was done in your first section. Then you started controlling your ISR. Next task is with respect to your scheduler, the locking and unlocking of the scheduler. So again we are using this locking and unlocking so that your critical section, they continues their execution without transfer of processor control to any other task. So to ensure this critical section execution, we are using yet another mechanism, the locking and unlocking the scheduler. So what are the functions that we use? Just two functions, right? Lock and unlock of what? The schedule. So OS schedule, sched lock and the OS get unlock. So see the lock function, this will disable the preemption by a higher priority task, right? So your task or the critical section cannot be preempted by a high priority task. You have locked your processor, and this function they can just as I have said, they inhibit the preemption by a high priority task, but they does not inhibit the interrupt. So when an interrupt occurs, this locking enables the return of your OS control to that task, which will execute this function, and the control return to your task after the ISR is complete. So when an interrupt comes, what happens? Your critical section will give control to the ISR, and once that function is completed, they get back the control. But that doesn't happen in the case of high priority task. So the OS get lock will disable preemption by a high priority task, right? Now what will happen in the unlock function? Just the opposite. They will enable the preemption by a high priority task, right? And if here in unlock condition, if an interrupt executes, then after the end of the ISR, the high priority task which is ready will execute after completion of ISR. So here we can see that they do not block the interrupts, they are blocking the high priority, blocking or enabling the high priority task. They always give preference for interrupts, not for high priority task. So once you have locked your critical section, you cannot, there will be disabling of preemption by a high priority task, but they can still accept interrupts. Just the opposite happens in OS schedule unlock. So in the three sections what we found that if there is a function which do a particular task, there is another function which will do a opposite task. So here you only have to study one task, there will be another opposite task, just the opposite functions. So it's easy for you to relate and remember, right? Okay. Now the fourth type of system level function is the get and set time functions. So as the name suggests, these functions are used for setting the time and getting the time. Now what does this time indicate? See, in the initialization stage, we had a method to initialize the clock ticking, right, the system clock tick. Now the time is the terms of number of system clock tick. The number of system clock ticks is your time. So you want to get the time, you want to set the time. So for that you will definitely again have two functions, the OS time set and the OS time get. So when you are setting the time, there is no return value, right? You are setting, you are passing some parameter. So it may be a 32-bit integer for the count or something like that. And when you are getting the time, what do you get? You are passing the current number of ticks as an unsigned integer, right? So this is what the micro OS does in the system level function. So the system level function was based on initializing the system, handling the ISR, and for handling the ISR you had different techniques, the lock and unlock technique, and finally you were here to set and get your time functions. All these things were handled in the system level functions in a micro OS. So this session was about MUCOS or the micro OS. So we saw the basic functions and features of micro OS, why they became so popular, their features. We had a detailed discussion about that. We also saw what are the source files, the processor dependent and the independent source files that micro OS uses, and later we stepped into the various functions that your MUCOS uses, and we discussed the system level functions in this session. In the next session we shall discuss other kind of functions that the MUCOS support. So for this time, thank you. See you in the next session. Have a great time.